one of the neat things that calculus teaches us is about how to recognize extreme values on interval. So extreme values, or extrema, are these ideas where a function has a rapid change in behavior. So if we look over here, we see that a function may be going up and then stop and then start coming down and then stop and come back up. And these behaviors of a function can actually be detected using the techniques of calculus. And to do that, we're going to recall a few facts from pre-calculus and before and start laying the groundwork for how we're going to use calculus to solve these. The first is the idea of a minimum and a maximum. So if I have a function and it's defined on some interval, so some a to some b, right? And if it contains, so if that contains some number c, then we can say that f has a minimum at that number if all the other values in that interval, all the function outputs are above f of c. It's a lot of words, but ultimately it's saying if you take an interval and you find a point that when you evaluate the function there, everything else is larger, well, that's the minimum. And that makes sense, right? It's the lowest value. If every value is at least as small, if not larger, then it must be the minimum value. And similarly, the maximum is defined. That if I have a function and I plug in, if I evaluate the function at c, and all the values are either below it or right at it, then that value must be, that there must be a maximum there. This is very clear from a graph like this. If I look at this number 4, I can clearly see that the function value here is higher than the function value anywhere else, and so it must be a maximum. That's all we're really talking about here. Now there's an interesting result called the extreme value theorem that says that if f is actually continuous on the closed interval, then it must have a maximum and it must have a minimum. And you could end up with a situation where that's not true if it's discontinuous, because you could have it kind of approach a maximum and then all of a sudden jump down, and so it never actually hits a point that's higher than all the rest, because there's always a point that's a little bit higher except for where it's not. So the point really is that you have to have a continuous function to be guaranteed that to say it attains its maximum and minimum on the interval. But anyway, looking at a sample graph here, I want to talk a little bit about the types of maxima and minima that we're going to be discussing. The first one is a local or a relative maximum. So if we look at this first point here, what it says is that in this strip, in this sort of local neighborhood, this point is larger than everybody else. So he's king of his little hill. He's not king of the world, but he's king of his little hill. And if we keep going down to 2, what we find is a global or an absolute minimum. What that means is that there's no point in the entire domain of that function. There's no point or there's no value that the function outputs that's lower than this. Now, it might have an identical value over here, but then they would both be global minima. But the idea is that in a global or absolute minimum, there is no value that function outputs that's any lower than that. Now, 3 is a local or relative minimum. What that means is that it behaves kind of like 2, but it's only in a local neighborhood. So again, it's local. It says that it's not in the whole world, it's not the lowest, but around all of its buddies in the neighborhood, it's the lowest. And finally, we reach the global or absolute maximum. And this happens at this spike here. So I want you to notice 2 things. One is that, again, it's higher than any point on the graph. So it is the global maximum. But the second thing I want you to notice is that it happens at this spike. Now, if you recall, functions don't have derivatives there, because what you're going to see is the slope of the tangent line is positive, 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 and then all of a sudden there's this break, and all of a sudden the slope of the tangent line becomes negative. So you're going to have this disconnect with the limits. So it's going to be like one's going straight up and one's going straight down, and it never quite gets to zero. So even in those particular cases, we still might have a global or local maxima and minimum. I do want to point out that all global minimums are also local minimums and vice versa. If you think about it, again, in this guy's little neighborhood, he's the lowest. But in this guy's little neighborhood, he's still the lowest. In this guy's neighborhood, he's the largest. But in this guy's neighborhood, he's also the largest. So every global is a local, but not every local is a global. And hopefully that makes sense. And we're going to do some examples to try to polish this behavior.